Okay, so let's discuss an example. Here is the bicycle wheel, and you are going forward. So what is the direction of the angular momentum? To the left. Okay. So suppose I lean to the right. So what will be the torque acting on the wheel? You mean in this direction? Now I'm leaning to this side, to the right. My right, your left. So what is the direction of the torque? I'm asking you the torque. So if I'm leaning like this, okay, let's see. I'm leaning like this. So I'm exerting a force, upward force on this end, R cross F. So this force is creating a torque in that direction. I'm exerting a downward force on this end. That creates a torque in the forward, in your direction also. So the net torque created by these two bars connecting the wheel to your bike is creating a torque in the forward direction. I'm leaning this in this direction. Well, the angular momentum was pointing in this direction. This is the angular momentum vector. It is along the axis in this example. I have an angular momentum, I have a torque, so the angular momentum vector should turn in that direction. But angular momentum is always along the axis of rotation for such a symmetric object. So if the angular momentum vector rotates in that direction, that means the wheel should rotate in that direction. If I'm leaning to the left, my right, your left. So let's see. I'm just going fast. I'm just leaning. The wheel rotates to the left. I'm leaning to the right. It rotates to the right. I'm not rotating. I'm just, the forces I exert are up and down only. Well, let's see. Well, in the wheel, so let's see, if I rotate it in this direction, if I'm just pulling and pushing now, it also leans to the left and the right if I just pull or push. So, you are on the wheel, you are on the bike, riding the bike. You try to turn to the left or to the right, to my right. The wheel will lean to the right. So if you just hold your steering wheel, rotate it to the right, the wheel will lean to the right. If you lean to the right, the wheel will rotate to the right, well, to that direction. So if there is an imbalance in your weight and you are leaning to one side on the bike, if the bike is moving really fast, the direction of the wheel will try to adjust for it. So you will not fall down in a moving bike. So that's why the bikes are stable. Because if you lean to the left a bit or to the right a bit, they just correct themselves. And if you are standing up straight, almost parallel, you are creating negligible torques acting on the system. If the angular momentum is very large, if you are really going really fast, the angular momentum is really large. So just by a very small torque that you might create by some imbalance in your weight distribution, it will not affect the angular momentum of the system at all. So the angular momentum will just stay as it is. Well, this is kind of an no, okay, this is an example. It just falls down. But if you just start rotating it, it doesn't fall down so fast. So that's why it's stable. It has such a large angular momentum. Any possible weight distribution, weight imbalance, doesn't affect the angular momentum. If the initial angular momentum is in this direction, it should always remain in that direction. It can never fall. Yes. Kind of, not exactly. You see, there's also the, I mean, in a motorbike, You cannot go like this on a straight line. If you are taking a curve, in that case, you can just lean to one side very strongly and at the same time go around the curve without falling down. So there's a uniform circular motion involved there. Hold on a bit. Just the motorbike example. No, it's a neat example. But you see, if this is the motorbike, it's just taking a curve. Okay, you have your weight, downward weight acting on the system. Plus, there are friction forces. There will be a friction force acting on the wheel in this direction. And are there any other forces acting? No, probably not. Okay, there are two effects. One is the torque, as you said. There is a net torque acting on the system now. But that means the angular momentum of the system should be rotating, but it does. As you are taking the curve, initially, if this is the curve, well, if you are moving in that direction, what is the direction of the angular momentum you have? So the wheels are rotating in this direction if you are going forward. So the angular momentum will be pointing in this direction. So this is the angular momentum vector. This is the initially when you enter the curve. When you are leaving the curve, this is the your angular momentum vector. So there is a net change in the angular momentum vector. So there should be a torque acting on the system due to your weight. Well, we have some torque acting on the system in this case. Well, you are right, in fact. It's only the torque. Yeah. Yes. Can you repeat your question? Shoot a bullet, okay. Okay. No, they are not. So this is me. This is the bullet. This is the bullet. This is a point mass. Moving some mass m with velocity v. So its angular momentum points in the outward direction. Its linear velocity is in this direction. Its angular momentum is in this direction. L is pointing inside the blackboard. Well, the angular velocity will depend on your reference point. If you just consider it as an object rotating around this point, then its angular velocity will be also moving in that direction. So you are saying that, okay, I have this object, it is moving in that direction and at the same time rotating like this. Okay. I don't know ballistics. I have no idea. Can they have a reason? Nothing comes to my mind. Well, it can be the other way around. What you want to have is, since it's, well, okay, the question is not rotation around this point, but this is your bullet or rocket, let's say. When you send it, to make it move in a straight path, you make it rotate also. So if you just take this object, take an arbitrary object, and fire it, you will realize that it quite rarely goes straight if you fire it quite fast, because there will be some deformations on the surface, some bumps somewhere, and the air, if it's moving with such a fast velocity, the air friction will become significant. The air friction will be non-symmetrical, so it will cause your fast-moving object to move left, right, up, or down. If you give it a spin in any direction, I don't think it will make any difference whether it is in turning clockwise or counterclockwise. So what you are doing is you are giving it an angular momentum. If it rotates very fast, you are giving it a very large angular momentum. Now, if you give a system a large angular momentum, it's for a very small object. If you have a very small object with some angular momentum, it will be really hard to create a significant torque acting on the system because the distances are small, so there is no torque acting on the system. If there is no torque acting on the system, in that case, the angular momentum should be conserved at all times. But angular momentum is always in the axis of the bullet. And the bullet, due to its shape, will try to keep itself parallel to its velocity vector. So if you have if the bullet goes in such a trajectory for some reason, initially it has such an angular momentum. At this point, it is moving in this direction. It should have such an angular momentum. If it doesn't go straight, this will be the trajectory of the bullet exaggerated a bit. But if you want to change the angular momentum from this orientation to this orientation, you need to create a torque. It is a very small object. You cannot create a significant torque enough to change its angular momentum from this orientation to that orientation. So it will not go through such a trajectory. It will go straight. It will go straighter, let's say. So that's why you give it a spin. I guess. Other questions? Now let's go back to this example that we had studied also on Tuesday. Now we had discussed this example. So I have a massless thin rod and two masses are attached to it in such a way. And we had said that, okay, if I have an angular velocity vector pointing in the upward direction, then the angular momentum of the system points in this direction. At this moment, of course. Now, as my object is rotating, the angular momentum vector should also rotate if I want to keep it rotating around the same axis. Let's just assume that I am rotating this object always around this axis, but that means the angular momentum should be rotating all the time. But if I have angular momentum rotating all the time, then I need some torque acting on the system. Well, the weight of the object or any other forces acting on the object will not create any torque. Well, the weight goes through the center of mass, so it doesn't create any torque. If there are no other forces acting on the object, there cannot be any torque, so the object cannot keep rotating around that axis. So what we should do is we should apply some forces at some points. So we cannot, you see, if the object is rotating like this, or you have this rigid rod rotating like this, right like this, so angular momentum, it starts like this in this orientation, and then it will keep rotating. So at this point, I need a torque pointing in that direction. I need to create a torque in that direction. Well, these forces are enough to create such a torque acting on that direction. Now we can apply that principle to our wheel. So this is my wheel. If I rotate it, well, there's no such an imbalance. The angular momentum vector, this already tells me that the angular momentum vector of this wheel is pointing in the axis of the rotation. So the axis of rotation is fixed, angular momentum is fixed, there are no torques acting on the system. But if I go ahead and attach some mass here and attach another mass on the other side, it is just like adding such a system to this wheel system. We had just seen that in that case the angular momentum, the angular momentum of this system will be the angular momentum of the wheel plus the angular momentum created by the additional masses. But the additional masses do not create an angular momentum along the rotation axis. So the angular momentum created by the additional masses that I attach, one here, one on the other side, will be pointing in some other direction. But that means I have to exert some extra force on my system. in those directions to keep my system rotating along the same axis. Imagine that this is your the wheel of your car. You have probably heard of the balance adjustment, balans ayarı. So you have to take your wheels to adjust their balances from time to time. Well, what happens if the balance is not adjusted properly is that your angular momentum vector will not point in the axis of rotation. So for some reason you might have received some bump over here so that the mass distribution here will not be symmetrical around this axis. In that case, the angular momentum vector will not point in along the axis of rotation. And in order to keep your wheels rotating around the same axis, you have the axe that connects to your wheel should exert additional forces on your wheel, but that means your axe will just wear out in time. So that is why you have to do your balance adjustment, so that the axe will live longer. Any questions on these? Well, okay, on Tuesday we did one example of an equilibrium. Now, if you remember, we had studied the problem of a person leaning on a wall. So if you just lean on the wall, there are various forces acting on you, and you can obtain these forces by just requiring that the net torque acting on your system is 0, the net force acting on your system is 0. So that those two conditions are enough to obtain all the unknown forces on your system. Now that is those two are general conditions for equilibrium. So if these two conditions are satisfied, then your system will stay as it is. It will not rotate, it will not move, it will just stay where they are. Well, there are various systems that you would like to have these things. Well, one is if you are carrying weight. Well, this is kind of a trivial example. If you have, well, this doesn't have anything to do with rotations. If you have such a system of strings, then you know that everything will be stretched. So there will be some tension here, another tension here, and all of these will be stretched. So if you just consider this point, the net force acting on that point should be 0 because that point is not moving at all. So that just gives you the tensions in each one of the strings. So there, if you just take that point, there is T1 in that direction, there is T3 in that direction, and the T3 is the magnitude, there is T2 pointing downward. If this angle is theta, just saying that the vertical force is 0, it tells you that T2 should be equal to T3 sine theta, and T1 should be equal to T3 cosine theta. And then you have the mass. Your mass is also at rest. Just a free body diagram. You have the mg. You have a T2, well, minus T2 prime, let's say. Its magnitude is T2. And this tells you that T2 is equal to mg. And these are enough. This gives you T2, and once you know T2, you know T3. Once you know T3, you can find T1. This is kind of the trivial example. On Tuesday, we did an example where we used the torques only, and now we have the forces. Yes? Well, T1 and... Okay, so let's see. There is probably some mistake. No, T1 is T3 cosine theta. Now that is probably T2. That should be T2, not T1. There's a typo over there. No, not T2. That is T1. Yeah, no. T1 is equal to T2 cotangent theta. Or mg cotangent theta. A typo. Well, this is a more interesting example. Now, just like the similar case we had in the case of the leaning on the wall, if you just imagine that you have a bridge, it is supported at 2 points. Its mass is, let's say, capital M. And then there's a truck moving on top with mass small m. Let's say the truck is at a distance x, and the total length of the bridge is L. Of course, in this case, you don't want your bridge to move around. You don't want your bridge to rotate around. You want it to be stable. Furthermore, you would like these points to be strong enough to carry the forces that will be exerted on them. So you need to find what will be the maximum forces acting at these points. Let's call this N1. There will be another force acting here, N2. We have the total weight of the bridge, capital M, and the weight of capital Mg, and the weight of the truck. And what we would like to find are the N1 and N2. What are the forces N1 and N2? Yes, we will calculate the torque. We can calculate the torque around this point. If we calculate the torque around that point, we will obtain an equation that will involve small m, large m, both of which we know, and the N1 force, which we do not know. Question? Well, the torque you can calculate with respect to any point that you like. It's completely up to you. I mean, you can calculate the torque relative to this point. The torque relative to that point should be 0 because my bridge shouldn't be rotating relative to that point. Or you can say the torque relative to this point should be 0 because my system shouldn't be rotating around any point. So the torque with respect to any point should be 0. So do you prefer to calculate the torque relative to this point? Relative to this one? To this one? Okay, so you prefer to calculate the torque relative to this point. Okay, let me first do it my way, then we will do it your way. My way will be shorter. Let's calculate the torque relative to this one, this point. Well, the masses I know. N's I'm looking for. If I calculate the torque relative to that one, I will obtain an equation that contains N1 only. I have a single equation, single unknown. I can solve for N1. Then I will calculate the torque relative to this point. But that will not include N1, it will include N2. In that case, I will be able to find N2. If I write the torque relative to this point, it will contain both N1 and N2. So I will have one equation, two unknowns. I will have to write another equation which involves two unknowns, two equations, two unknowns. It will be more complicated to solve. Let's first start with this one. Well, what is the direction of the torque created by this weight? What is the direction of the torque created by this weight? with respect to this point. What is it? Well, let me also draw it. Okay, this is x. This is x, this is y, this is z. X, y, and z. So the torque created by this weight is r cross f relative to this point is in the minus z direction. So let's see, the net torque acting at that point, O, with respect to that point, O, is equal to, in the minus z direction, it's in minus z direction, and the magnitude is mgx, the force times the distance. They are at 90 degrees with each other, so sine of 90 is just 1. Then we have the torque created by this force, the direction of this torque, same, plus mg L over 2, plus the torque created by this force. Which direction is it is in? It's in the z direction. So it's plus m, no, not m, n1 times L. And this should be 0, because my system is not rotating. So this already tells me that n1 should be equal to mg over 2 minus mg x over L. Plus mgx over L. Sorry. Now let's write the torque relative to the point P. We know that it's in the z direction, plus or minus. So we are writing the torque relative to P. So what is the torque created by this weight, the weight of the bridge? The direction plus that mgl over 2. The torque created by this weight was its direction plus that plus mg L minus x, and the torque created by N2 minus that minus N2L. And this should also be 0 because my bridge is not rotating around the point P. So this tells me that N2 is mg over 2 plus mg 1 minus x over L. Now let's calculate the way that Thailand proposed. Let's see what we get. You see, in principle, we get a different equation for any point that we choose. We can choose the center of mass, you can choose this point, this point, this point, any point that you like, and that gives you another equation for the torque. There were a few things that you learned in high school that were correct. Now let's write the torque relative to that point. What is the direction of the torque created by N2? Minus that. Torque relative to the center of mass. Its magnitude is N2 L over 2 is in the minus z direction. Now the torque created by this one. Well, it's in the z direction plus mg L over 2 minus x. Well, this distance is L over 2, this distance is x, so what remains is L over 2 minus x. Now the torque created by mg, 0. The torque created by N2 plus that direction plus N1, well that's N1, L over 2. So our n1 and n2 should also satisfy that relation. This should be 0. Let me look at this one. Is this equal to torque around the point O plus the torque around the point P divided by 2? So if I just add these one up, I get N1 L over 2. Well, it's in the torque around the center of mass. I get minus N2 over 2, L over 2. I get, that is the first term. Now, if I sum the remaining terms, I have minus mg L over 2 plus mg L over 2. So these two terms, they cancel each other. If I add these two, I have, and divide by 2, I get mg L over 2 minus x. And that is over there. So if I take this point to calculate the torque, the net torque I obtain is nothing but some linear combination of these two. And since each one of these are 0, this is automatically 0. Now, if you have two unknowns, then you need two equations to solve it. If you have one equation only, you cannot solve for your unknowns. If you have three equations for your unknowns, for your two unknowns, in that case, you might not have any solution. So that is why, in fact, this was a nice example. We have a third equation here. We have a third equation that our unknowns should satisfy. So in principle, it is possible that such a system doesn't have any solution, because we have two unknowns and three equations to satisfy it. Just two unknowns give me two equations is enough to determine my unknowns, and my unknowns need not satisfy the third equation. But if you take any other point, in fact, if you take this point or any point somewhere in between, you obtain another equation, but that equation is nothing but some linear combination of these two equations. So they do not really give you a third equation. It's just some combination of these things, so that we still have solutions. Any questions? Okay, we have 3 weeks left. And it is like I have 4 topics that I would like to cover somehow. Okay, what I will do, now, we will not go, okay, up to now, all chapters we covered in detail. We didn't skip anything in all the chapters. But I would like to spend 1 or 2 hours on oscillations. Not today. 1 or 2 hours on oscillations. It will be on Thursday. The Thursday 2 hours I will be doing oscillations. On Monday, on Tuesday, our 3 hours I will be doing fluid mechanics. Just to give you an idea, not to learn it in detail. I know that some of you are doing projects on fluid mechanics. Some of you would like to work on fluid mechanics in the future. So that's why I would like to tell you, okay, this is fluid mechanics, just an introduction, not in detail coverage. And in the last 2 weeks, we will do some thermodynamics. We can do some extra classes, but after the 3 weeks, it's your final time, and none of you will be volunteering to come. After the finals, if there are any one of you interested in studying anything related with these things or related with other stuff, we can continue with that. But you just organize yourself, form at least a small group of at least 5, then we can continue if you are interested. Of course, it will not be relevant for the final. It will not be subjects of the next semester, but we can continue during the semester break. Any questions? Oscillations for next week. Next week, On Tuesday, we will be doing some fluid mechanics. As I said, it's just an overview of fluid mechanics. And on Thursday, we will have these oscillations.